Hey, Carly.
Hey, Waf, what are we doing today?
Today we're going to look at the probability mass and probability density functions. These are functions on distributions that help us identify what the density of one particular part of the distribution is.
Ooh.
And unlike all the other functions, this function actually has a different name and a different call depending on if it's a continuous distribution or a discrete distribution. When we have a discrete distribution, we have a probability mass function, or a PMF. And this function is only defined in discrete distributions where each event has a fixed probability of occurring. On the other hand, a probability density function, or PDF, is defined only on continuous distributions where finding a particular probability needs to occur within a window in time. So if for every single distribution, we can have any sort of distribution we can use. We can use a normal curve, a Bernoulli distribution, a binomial distribution. And for here, I want to have a distribution using dice. I want to know if we have a dice, how many times, if I roll this 10 times, will I get a 6? I want the count of number of 6s I'm going to get. So since 10 events are happening, this seems like n equals 10 rolls. And Carly, what's the probability of getting a 6?
1/6, and this
1/6.
seems like a binomial distribution because we have n and p.
Exactly. So this is a classic binomial distribution. We have a success with a probability of 1/6. So I'm going to have to import, or sorry, from scipy.stats, I'm going to import the binom. And then I'm going to go ahead and create my classic distribution D is equal to a binom of n equals 10 and p equals 1/6. And this is a distribution of this, how many times a 6 will appear when I roll a 6-sided die. And I have a histogram of this distribution right here, but I want to find out some information about this. So I want to know the probability of getting no 6s. So we've actually done a calculation like this mathematically.
Yes.
But now this is represented in the histogram as whatever the size of this particular bar is, the bar of 0 6s. So this is where the probability mass function, how much mass is there this bar, is going to help us out. So I'm going to do d.pmf, and I want to know the probability mass function of the value 0. So d.pmf of 0.
And we get 0.16.
0.16. So looking at this graph, it's right above 0.15. So there's a 16% chance of me rolling 10 dice and getting no 6s. What about the probability of getting exactly 1/6? So that's going to be d.pmf of 1. And what did you get, Carly?
0.32.
0.32, or 32%. And again, that's the probability of getting exactly a 1. So that's the mass of this particular bar. And what about getting 2 6s? That's going to be d.pmf of 2.
2, and that gives me 0.29.
0.29, or 29%. And then what a probability of half our 6s? So half my rolls are 6s, so we have d.pmf of 5.
And we get 0.013.
0.013, so only a 1.3% chance of 5 of my 10 dice being 5. So this is exactly getting 5 6s, not getting more, not getting less, 1.3% of my outcomes. And what about the probability of getting 10 6s, all 10 6s? So d.pmf of 10.
So this one is tiny. It's 1.65 times 10 to the negative 8.
1.565 times 10 to the negative 8. So we can move the decimal to the left 8 points. So this is the same as saying 0.000000165, which is way, 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 way less than 1%, less than 1% of 1%. And you can see on this graph, I can't even see any blue at all. The probability is that low, but that is the width or the density of that particular part of the bar. So a tiny, tiny fraction. It is possible, but it's very, very unlikely to get 10 6s. And here's the last one, the probability of at least 3 6s. So how would you approach this, Carly?
Ooh, so if this was a statistical probability question that I was calculating, I would think about, okay, at least 3 6s. That's one of those special cases where it's complicated to calculate that directly, because at least 3 6s means I could get 3 6s or 4 6s or 5 6s all the way up to 10 6s, and that seems a little much. So I would do 1 minus the probability of getting
0 sixes, 1 sixes, or true sixes,
Yeah,
right?
yeah.
You'd
I
add
was
up
like,
everything
how
to
do
the
I
left
say
of
that?
it.
Basically, of everything else besides the 3. So yeah, 0, 1, or 2.
Awesome. So I think we can do 1 minus the d.pmf of getting 0 sixes. And still inside this parentheses, because we want to minus the sum of all of them.
Ooh, okay.
D minus PMF of getting 1 6 plus D minus PMF of 2 sixes. So we're taking basically 1 minus the density of the 0 bar and the 1 bar and the 2 bar. So does that make sense on how you apply your rule?
Definitely makes sense to me. And when I go ahead and do that, I get 0.22.
0.22, so there's a 22% chance of getting at least 3 sixes. But I also think about another function that we just recently learned, which is the CDF. So the CDF says how much of the bar have we seen to the left of some certain value. So I know at least 3 sixes means that I need 3 sixes or more. So I want to know how much is to the left of something before 3. So I'm going to do d.cdf, so the cumulative distribution function, of everything to the left of 2.5. So that's going to be at least 3, so that's not going to include, so that's going to be 0, 1, and 2, but I want to know everything that has at least 3 sixes or more, so I'm going to do 1 minus to get the right-hand tail of everything that has 2.5 or more sixes.
And I get 0.22 as well. I get the exact same answer.
Or 22%. So you can see the PMF is kind of a one specific point of the curve, while the CDF is everything to the left, or 1 minus CDF is everything to the right. So we can see that they're actually interchanged with each other. That if you want one particular point, PMF is the way to go. If you want the entire area, you can use CDF. So whenever you see at least or at most, you're often going to want CDF. If you want to know exact, you're often going to want the PMF.
Exactly.
So PMFs only work on discrete distributions. So there's a problem that comes up when we start looking at continuous distributions. So for the continuous distributions, we're going to have to use something called a probability density function. And the reason that we can't just use a probability mass function, or a PMF, is the fact that for a continuous distribution, if we want to know the actual point at something along this distribution, the area underneath a single line is actually 0.
Yes, exactly.
So there's no area. You have to have at least a square to have an area. You don't have a square when you have just a single point. So that area is actually 0. And we can think about this as the fact that if we think about a sunscreen product, so here's the example I have. The amount of time that sunscreen provides protection from ultraviolet rays is normally distributed. Specifically, one sunscreen provides SPF 30 protection for an average of 6 hours with a standard deviation of 20 minutes. So if we convert these to z-scores, that means a z of 0, 0.000000, and exactly 0 is exactly 6 hours of sun protection. But a z-score of 0.002, so if we just move a tiny bit over, that is giving you sun protection of 6 hours and exactly 1.2 seconds. So the probability of any one of these events being true is effectively 0. So your sunscreen may stop providing SPF 30 protection at 6 minutes and 32.817 seconds. Your particular sunscreen will have a particular point where it occurs at, but the probability of that point is going to be a distribution. It's not going to be a fixed probability where everyone's in the same bucket. So for that, we want to find out what is the probability of being around a certain point. So the probability density function gives us the probability of an event occurring in a distribution around a particular point. And we're going to use the standard normal distribution to help us analyze the sunscreen to know what's the probability of different events occurring within the context of the sunscreen. So let's look at a simple normal distribution. So I'm going to go ahead and create a normal distribution by saying from scipy.stats. I'm going to import norm. And then I'm going to say d is equal to my normal distribution. So I'm just going to use a standard normal distribution. So we're going to need to convert everything to z-scores to work out from here. So what is the prediction of the sunscreen expiring around 6 hours? So to do that, we're going to have to convert 6 hours to a z-score. So Carly, 6 hours is exactly the mean of the distribution.
Yeah, so the z-score should just be 0.
So I want to know what is the distribution, what is the probability density function, the PDF of 0?
And it is about 0.4.
So 0.39 something, right?
0.3989.
Yes, 3989. Awesome, right around 0.4. So 39% or 40% of all sunscreen wearers are going to see their SPF protection run out around 6 hours. So what about the probability of people seeing their sunscreen protection ending a little early at just 5 hours? So we have to convert that to a z-score.
Yeah.
So how would we convert this to a z-score, Carly?
So let's see. So we know that our z-score formula is just value minus average divided by standard deviation. And we know our value is 5.
We know our average is 6.
Yep. And I think the standard deviation was 0.2.
Well, it's 20 minutes. So
20 minutes.
So that's a third of an hour, right?
Yeah.
So our standard deviation, because the units have to be the same.
Right.
So even though it's 20 minutes, we won't divide by 20. We divide by how many hours since it tops hours. So 1/3, is that right?
That sounds right.
So if we do, well, just that's -1 on top divided by 1/3. So that's going to be -3. So we have a z-score of -3. So if I want to know how much percent of people have their sunscreen expire around 5 hours, I can do d.pdf of -3. And how many people? What percentage of people do we have?
So we get 0.0044.
0.0044. So 0.44% of people, less than half of 1%, have their sunscreen expiring after 5 hours. So one other question is, what can be the probability of the protection lasting at least 5 hours? So at least 5 hours means that we want to find where the z-score is at, so here's 0, -1, -2, -3. So we're over here. We want to know everyone's whose sunscreen at least lasts 5 hours. So this is going to be all the area to the right. So I know I need to do 1 minus d.cdf of -3.
And we get 0.9987.
99.87%.
So almost everyone.
Almost everyone. So analysis. If you were a science advisor, how often would you recommend reapplying sunscreen based on the data provided to ensure continuous SPF 30 protection? So if you were a science advisor, what would you say? Would you want to replace it every 6 hours, or would you want to replace it every 5 hours to ensure that people were safe?
I think every 5 hours to be super conservative.
Yeah, so I would say 5 hours, because we know that the sunscreen will still be working after 5 hours in 99.87% of cases. So nearly everyone will still have active sunscreen protection after 5 hours. But if we wait all the way to 6 hours, half the people have lost their sunscreen protection.
We don't want that to happen.
So these are the analysis you might do as you're making decisions about products. And maybe you want to be even more conservative. Maybe having 0.13% of people getting sunburnt isn't acceptable. Maybe it should be reapplied every 4 hours, and we can run the statistics on 4 hours. So there's a lot of science that goes into this stuff, and distributions help us do this. And the PEMF and the PDF are functions that tell us the precise value at particular points within a distribution.